So, starting off from where we left off in the part A of the lectures. Um, so the next what we aim to calculate is a quantity uh, which is the expectation value of log P. What is P? It's the probability of being in different microstates, right? And this H is not Hamiltonian, but it was just called H by Boltzmann, so we're going to call it H. And this is the expectation value of the ln of the probability of being in different microstates. And nowhere am I assuming here that all the PRs, the probability of PR of being in a particular microstate is going to be the identical. So just reminding you that this H is not Hamiltonian, and so the way you calculate expectation value of any quantity is take that value of that quantity, ln of PR in this case, and R can be any microstate or any state if you like, in the probability of accessing that state. Now this PR can change as a function of time in general, and correspondingly H is going to change as a function of time. And moreover, for different values of R, different values of microstates, if you like, PR is not the same. So PR1 is not equal to PR2 is not equal to PR3 in general, because nowhere have we assumed equilibrium. We're just saying we've taken a system, PRs are different for different microstates. We have isolated it, and then we are calculating some quantity called H, and let's see how it changes as a function of time. So what we are going to do is, okay, so I'm going to move this first of all, else maybe move it here. Okay, Control N. And yeah. So del H del T, rate of change of H with time, is del PR dt ln PR. Right, we are just differentiating this quantity with respect to time. Ln PR is remaining intact. Then PR into ddt of ln PR, and this will give 1 upon PR, because a derivative of a ln, and then dPR dt. This PR and this PR cancels. So what we have is this term remains. So we take dPR dt out of the bracket ln PR plus 1. This gives this plus 1. And you have the ln PR here, and summation over all R. Now we have dPR dt, right? Rate of change of probability and state R as a function of time, and that we are going to use the master's equation to write it down as summation over all S, WRS, right? And WRS is equal to WSR because energy is constant. We are looking at an isolated system. PS minus PR. So this is increasing PR, right? And this term is decreasing PR. So WRS minus PR is going to decrease PR. PS minus PR ln PR as was there plus 1. Now this expression is being written in two ways. On one hand, I'm going to write it, this is just an algebraic manipulation. We'll see the reason, because we'll write it in a certain form. So all our attempt is to write it in a certain form and figure out whether del H del T is increasing, decreasing, or what is happening. So on one hand, we are rewriting PR minus PS and taking out with a minus sign. So here we have written PR minus PS, and here there is a minus sign. Summation over R, summation over S, ln PR plus 1. Also, this R and S are domain distance. I mean, if we wished, we could have written dH dt equal to summation over S, all microstates into dPs dt ln PR da da da, and then this del PS dt we could have written as PR minus PS. I mean, so if we exchange these two indices, so from here, on one hand, we are taking out minus sign. On the other hand, we are exchanging S and R, and correspondingly, you would get WSR PR minus PS ln PS plus 1, right? So this we are rewriting once like this and once like this, where R and S are interchanged, and correspondingly, this has become PR minus PS. Okay. Now we add this and this. So this is also DHDT. This is also DHDT. We are adding that. So 2 DHDT. And taking out this minus sign, right? If we take out the minus sign, then what you get is 2 DHDT equal to minus W. So basically PR minus PS. So in both you have PR minus PS, PR minus PS, right? But we have taken out the minus sign. As a consequence, we get ln PR minus PS. So if you put this here, you will again get plus PS, right? But we have taken it out intentionally. And what we have achieved by writing it like this is we are writing PR minus PS and ln PR minus ln PS. Now, if by any chance PR is greater than PS, then this is a monotonic function. Ln is a monotonic function of any quantity. So if PR is greater than PS, then ln PR is going to be greater than PS. Both are positive, right? On the other hand, so if PR is greater than PS, this is also positive, and the product of two is going to be positive. On the other hand, if PR was less than PS, so this would be negative, so would be this, and the product of the two will be positive. So whatever is there under the two double summations is always a positive quantity as PR and PH change, right? I mean, they might change or might not change, but in general, it's so dH dt is going to keep on changing, and dH dt is also related to dPR dt ln PR. So if dH dt changes, and it becomes more and more negative because this is a positive quantity and you have a minus sign sitting here. So this is the algebraic manipulation which we are doing. We're writing it so that this term into this term is always positive. So that's what we have done, and there's a negative. So, so these things inside the summations are positive. The dH dt is always changing. This is going to drive the PR. This is going to drive change in the values of PR as well, right? And the point is dH dt will keep on decreasing till dH dt equal to 0, and in that case, that can be 0 if only if all the PRs equal to again PS, right? Because if any of them are unequal, dH dt will keep decreasing. If dH dt keep decreasing, then this PRPT will, if they are unequal, they will keep changing, and they will keep changing till PR is equal to PS. And once they are equal, all the different probability of different microstates are equal, then dH dt cannot decrease anymore. It is equal to 0 and will remain equal to 0. And that is the condition for equilibrium. Hence, only when all the probability of all the microstates of isolated system. This was defined for an isolated system. They remain unless they become equal, this quantity will keep on decreasing till it has reached its minimum value, and it will reach its minimum value when PR, the probability of all occupation of all the microstates are really equal, and then it can't change anymore, the system cannot evolve anymore, and then you have got equilibrium, and that is the input to postulate of equal a priori probability, right? So that was the discussion for isolated system, which defines the macrocanonical ensemble, and from there we go to the canonical ensemble. We'll just look at the Master's equation from the for the canonical system as well, because even if the system is in equilibrium, then we know that PR is not equal to PS, right? The probability of different microstates are not the same if the energies are different. Only if the energies are the same, the probabilities are the same, and therefore, and if and if there are transitions from one state to the other where the energy is not equal, WRS need not equal to WSR. In fact, the Master's equation can be written as dPr dt equal to summation over all S. I mean, PS, probability of occupation is a particular microstate, the transition probability of WSR, S to R, and this is R to S, right? And when energies can change, these need not be equal because HI need not be Hermitian, and so on and so forth. As a consequence, in equilibrium, in a canonical system, you will have equilibrium only when, in terms of the Master equation, not only dPr dt equal to 0, but again there is no probability current from any particular pair of states. That is, each of the terms under the summation, suppose you had a bracket here, so here, right? So each of the terms PR into W, so basically PR into WRS minus PS into WSR, it's okay, and they have to be identically equal to 0 for each of the individual terms. And in that case, you automatically get that the transition probabilities, the ratio of transition probabilities, WS to R to W, R to S, has to be equal to PR by PS. So basically, you're rewriting this PR by PS, yeah, equal to WSR by WRS. So this is the so now this is the principle of detailed balance, and so basically, if you have a system in non-equilibrium in the canonical system, then you will have your microscopic WSR and WRS, and the occupation or the probability of accessing different microstates will keep on changing till this relation is holds. And once this relation holds for each of the terms, then dPr dt will become equal to 0. On the other hand, if each of these terms independently were not equal to 0, but only the sum of the terms was equal to 0, then it is not, then the system is not in equilibrium. There is a net probability current from one set of microstates to another set of microstates, different energies, the same, whatever be it. And then the system is in steady state and not in equilibrium. So so for it to be in equilibrium, this has to hold for every pair of states, so that each individual term are identically equal to 0, no probability current, and all the PRs and all the probabilities might be different, but they don't change as a function of time. So that's the end of this module. So let me stop